and welcome back to Calculus 1. No, Calculus 2. I gotta start over. Hello and welcome back to Calculus 2, section 7.2, integration by parts. There we go. So, as I mentioned earlier, this is extremely important method of integration. And we're going to discover what's it all about. Let me just first show the scenario when we have to use something like this. So say you have integral of x times x minus 1 squared dx. Sure, you can do u sub here, which would be that back substitution, which would actually just complicate things for no reason. And you definitely can FOIL, right, x minus 1, and then multiply through by x and solve it. So there are two, should I say easy, right, ways to integrate something like this. And just the sheer fact that you can actually multiply it out, work this x minus 1 into x squared minus 2x plus 1 and then times x, right? So this can be easily done by just simply, right, it will be x squared minus x cubed minus 2x squared plus x dx when you multiply everything out, and then it's easy, right? But then we say, all right, what happens if I have functions that are not compatible? So you say, all right, so how about if I put this? What do you do now? U sub for x squared, still easy, right? So yours is easy. U equals x squared, du equals 2x dx. And by basic u sub, you are done in a step. But then, this shows up. Yes, exactly. Tan, 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 tan. Right? No, just nothing can be done here. Can't multiply it through because it's exponential function and linear function. So they're not compatible, right, for multiplication. Can't do u sub because integral the u sub for for x is just x, right? We have derivative of that is 1. We still have extra x. Back substitution doesn't work, and none of the methods that we did in splitting the integrals, none of the stuff works. So what are we going to do here for this particular integral, right? So this is the one that is going to be done by integration by parts. And you are going to see that we are going to have some very interesting integrals solved by this technique. But let's first figure out what this technique is. We are all familiar with the fact, hopefully, that integration are backwards derivatives. So we know that derivative of sine is cosine, integral of cosine is sine. We know that the integral of ln x, integral of 1 over x is ln x, and the derivative of ln x is 1 over x. So they're backwards. Now, what was u sub? Does anyone know in the core, right? What is u sub? U substitution. Reverse chain rule. Very good. So when we had the u sub, when you had the chain rule, you would say that the derivative of e to the x squared is 2x e to the x squared, right? And integral would be just backwards of whatever you had. So now, what is the product rule? What is the integration by parts reverse? It's actually the product rule, right? So you cannot separate integrals over the products and quotients, just like you can't separate derivatives over products and quotients. You are only allowed to do that for addition and subtraction, write separate integrals. But if you have multiplication of two functions, like you have over here, you have multiplications of two functions, the only thing that you can do is integration by parts. Might be later on, trig sub and stuff, but you cannot separate into two integrals over the product because it's just wrong. So since I already told you that this is backwards product rule, let's develop the formula starting at the product rule. We know that u times v, the derivative, is equal to uv prime plus vu prime. So that was the formula which you memorized. Now I'm going to write this in a little bit better form, and I'm going to use f and g. So f times g, the derivative of f times g, is equal to function f times the derivative of g plus function g times the derivative of f in respect to x. So this is if you write it out using Leibniz notation. Now, what do we want to do? Well, I want to integrate this. So I'm going to integrate everywhere, and when you are integrating, you are going to introduce integral and then dx and then integral and then dx and then the integral and then dx. So what happens? What happens is that in the first case, the integral cancels with the derivative, so these guys drop, and you are left with f times g. On the other side, dx and dx drop, and you have integral of f of x dg, which is what? So what do we get? Actually, no, wait. No, we don't, let's not cancel it. Let's just leave it as is. So what do you get? As you integrate, what do you get? Integral of, you don't integrate. This is what you get. I should put of x. Now, it doesn't make a lot of sense, but this is actually the product rule reversed. Now, if we are to write this in terms of our uv above, I will do the same, except now it's going to be a little bit loose notation. As I integrate everywhere, what I get is u times v is equal to integral of u dv plus integral of v du. Now, this v is the function of x, and u is function of x. We just don't put of x throughout. So what is the integral of this? We are going to now rearrange this and make it into integral of u dv is equal to u times v minus integral of v du. This is known as the formula for integration by parts. The reason why it's called integration by parts is because you have part number 1 and part number 2. There are 2 parts. And then you compile the second portion over here, which I will explain how it's done. If you're still not happy with this, here's my final offering for you to understand what's going on. I'm going to draw in the UV plane a function. Now this is clearly a function of, right, this is function v in respect to u. And now I'm going to take a look at area 1. Area 1 is clearly integral of function v in respect of du, because remember how you're looking for the area and this was dx, but now it's the u-axis, right? So it's du. Because that one had the vertical representative rectangle which was swiping from the left to the right over all du values. Area A2 is going to be done this way, and that's dv. So that's integral of u dv. I hope you see that when you add them, you get this. But in reality, you have a rectangle here, which is u times v. So the overall area is u times v. And we see that area is equal to area 1 plus area 2, which is integral of v du plus integral of u dv, which leads to our formula eventually that integral of u dv is equal to uv minus integral of v du. So this would be some kind of graphical approach to the proof. And we just derived this. So integration by parts, it's backward product rule. So now let's solve some problems with it. Lots of problems with it. Not some. So we start with x e to the sine x, sorry, dx. It's my favorite example to start. Clearly, I can't use algebra to multiply these first. So let me try and use my new formula because nothing else works. All right, so I'm just going to do this problem because I know how to do it. And you might have questions, why did you pick what you picked? And my answer to that is A, I'm divine, and B, I know this stuff. Those are my answers that I can give you right now. And we'll see later, you actually develop the skill as you keep working on these problems. This is something that you have to sit down and just do 5,000 problems to get the feel of what needs to be what. Now, there are some guidelines, but they don't always work, and we'll see. In general, we would like to use polynomial portions for u because the derivative would eventually kill it. So, that being said, I'm going to say u equals x, and dv would be everything else. Because u and dv have to take on all of it in the integral. Now, I said this 5,000 times already in this course. This dx is not there for decoration. It's the part of the integral, and it's the width that you are multiplying. So you better treat that dx almost as a function. All right? It's as important as sine x. It's as important as x. And you see it featured in the dv. It will always be featured within dv substitution. Always in dv, yes. Now, observe that I wrote this to the side of each other. So what I'm going to do now is underneath, what's du? It's dx, right? You take the derivative. And what's the v when you integrate sine? Negative cosine x. You don't have to put plus c in this case. There will be a major plus c at the end of the problem for 1 point. So if you write this in this fashion, the formula will just appear easily. So you write u here, and then dv, and you go down for the derivative, and you go down for the integral to obtain the other two. Now I hope you see that we have all of the ingredients for our soup. What is in my soup? u, dv, u, v, v, du. Right? I have 6, but only 4 of the variety, right? U shows up twice, V shows up twice, so U, V, du, dv. And I have all 4 of them. All I need to do is to put this together like Legos. Or the cake, whatever you are assembling. Now, look at this. There's your formula right there. uv minus v du. You see the arrow? Do we all see uv minus v du? That's why the arrow is there. So the integral is equal to u times v, which is negative x cosine x, minus the integral of negative cosine x dx. And I'm going to say this is u, this is v, this is v, and this is du. And that's the minus. Fix it, integrate, be done. What's the integral of cosine? Excellent. What happened? Plus c or minus 1, you can choose whatever. I mean, minus 1 or 10. No, plus c. That's plus c. Okay.
I hope so. Pretty sure I wrote plus C on problems with the lead plus C.
Just plus c on everything. One day you're signing off the check. Like,
I mean, you said it was minus 1 every time it didn't show up. So if it does show up, that's plus 1 point. So that's the credit.
yeah, I have to specify that as well. Here's the problem. It can't be done by U sub. It can't be done by regular basic vanilla integration because it has multiplication between two non-compatible functions. Can't multiply it. We pick polynomial part if it's present. Most of the time, it's okay. It's convenient. We take the polynomial part as U, and then the rest as dv, and then find the derivative, find the integral, and then just by drawing the arrow, you have your uv minus v du. As a formula, minus and minus is plus, just need to integrate this part, and here is the answer. Question is this correct? Is this true? And the answer to that is just differentiate. You differentiate this answer. If you get this, it's good. If you don't get this, it's garbage. Because in mathematics, the answers are either correct or or they're wrong. There is no kinda situation. So as much as I said that the second exam is trickier because you have a number of different integration techniques, one thing is a blessing or as a something that is awesome about it is that every time you are done integrating, you can take a derivative and check if what you got actually is correct. And the only thing that will prevent you from checking is your laziness or I don't care, right? So either one of those two would be preventing you from, because you all know how to differentiate, right? That's not an issue. The issue is just that laziness hump or I just don't care hump, like get out of here as soon as possible. So now I am going to check this because I care. And because we're live. So I'm going to differentiate the answer. And hope to get the original problem up there. So let's see. It doesn't look good, right? Because it has that like that plus sign x, right? Which will give us cosine. But then we realize that this over here is product rule. And that's going to give us extra terms. Whew, right? So copy the first, negative x. The derivative of cosine is negative sine. Awesome. Plus copy the second, which is cosine x, times the derivative of the first, which is negative 1, plus the derivative of sine is cosine x, and the derivative of plus c is 0. So now I have x sine x, because negative times negative is positive. Cosine times negative 1 is negative cosine x, plus cosine x, they die, and there it is, x sine x. So this is what it takes for you to check. Now, if you have a definite integral, you will do this before you compute, right? Because you would have a statement like this, and then maybe from, I don't know, from 0 to pi. Before you compute a number, you can actually perform the check procedure to see if you integrated correctly. And then go, once you know that the integration is correct, right, then you can go and compute with limits, in which case, you hope you don't make mistake on arithmetic, right, computation part. So that was that part. And now I'm going to ask you to do the same thing for e to the x. So integral x e to the x dx. So as I said, you use your polynomial part for u in this case. Okay, so what do we have? Same. This problem is exactly the same as the previous one. So that's the initial pick. du equals dx. V equals, again, e to dx. We put the arrow to help us with the formula. So we have uv, which is x e to the x, minus the integral of e to the x dx, which is x e to the x, minus the integral of e to the x is e to the x, plus c. And the problem is solved. Again, the product rule will create additional e to the x, which will cancel with e to the x. Derivative c is 0, so you get exactly the problem when you check. Let's take a look at one problem from the homework. All right, so here's one. This is problem 16. Integral of x ln x dx. So as you're picking u and dv, don't forget dx. You have to plug in under dv part so you can integrate. You can integrate without it. How's it going? Or not? So did you hit the brick wall yet, or it's all cool?
Trying it, but not getting very far.
Hurry up. All right, so we're hitting the brick wall, I hope, right? Because if you go with the standard, use the polynomial for u, so it dies in a derivative, you get stuck with integral of ln x. We don't know what that is. We don't know what that is. So if I go and I say u equals x, dv equals, I'm going to erase this, ln x dx, and then I go du is dx, and then you go v is, ugh.
Do we have to make
I don't know,
full U?
right? So I don't know.
So U equals L X?
Yes. So you run, you hit the brick wall, shake it off, run the other way. So now we're going to actually put ln x over here. And we're just going to use this one as x dx. Swap them. Go on. Let's see what happens.
Oh, right. Oh, and then that. Oh. Okay, so if they're on the phone, it's this really cool reusable pen, because this means that when your curve is like just this weird rubber thick, like superhero. That one, yeah. So like the eraser doesn't material.
All right, so hopefully you were all able to solve this problem quickly and efficiently because I gave you what you're supposed to do, right? So the derivative of ln x is 1 over x dx, and the integral of x is x squared over 2. We are going to put the arrow, and uv is x squared over 2 ln x minus the integral of x squared over 2 times 1 over x dx. Now that can be simplified and solved easily, I hope. So x squared over 2 ln x minus, we kick 1/2 outside, and we just have integral of x dx. So x squared over 2 ln x minus 1/4 x squared plus c. Now you can factor out 1/2 x squared and so on, but we're done. What was the hurdle earlier? We didn't know what was integral of ln x. So we couldn't do our favorite way, which is pick polynomial function to be u. All right, so let's figure out what's the integral of ln x.
Come on, you go for 2 seconds.
2 seconds are up.
It's like 45 seconds. It's just, be careful, but.
I'll put it on a cloud. That's -1 right there. All right. So we're supposed to figure out what's the integral of ln x. Finally, after all these years, right? So what is the integral of ln x? How am I going to do this? Well, we think, I know I can differentiate ln x. Therefore, has to be u, because u is differentiated. I'm going to go there and say it's common sense. You can't put ln x in a dv part because you would end up with this, and this is what you're trying to figure out, right, in the first place. So dv equals dx. Obviously, right? And now you just execute the rest. Go on. Where's your plus c? Oh, you add that later. Okay. Just make sure you can add that at any point before you hand in the test. Every later is late. Okay. What do we get? We get x ln x minus the integral of x times 1 over x dx, which cancels. I'll go next line. So x ln x minus the integral of dx, which is x ln x minus x plus c. And I'll put this for Alex in the cloud. All right, next question. Let's go back to easier stuff, like trig. What now? We can integrate both. We can differentiate both. Does it matter which one we pick as u, which one we pick as v, dv? We can integrate both, we can differentiate both. Does it matter? So let's think about it. The new integral will contain the derivative of this and integral of that. Let's say, if you pick it that way. The derivative of this is going to go down 1, and this is just going to stay in a sine cosine loop, right? Whether you differentiate or integrate, stays in a sine cosine loop. This one, you can either make better with differentiation or worse by integration. Because if you integrate this, you get x cubed. Integrate again, x to the 4th. None of them go away.
Eventually, that's going to root. And you just add it to the sum that you want.
Well, in this case, it's not going to loop. One loops, but x squared is going to die if you keep using it in the derivative. So let's go. Integration by parts again. Except this time, right? Well, you're going back to the u equals x squared. And then examine closely what happens with the integral that you still have to compute. I'll be right back. So what's interesting about, once you're done with the procedure, what's interesting about the integral that you still have to compute? You still need to do it one more time. Very good.
Yeah, okay. The second time, then another. Wait. Because right now I have x sine x plus x cosine x minus negative x cosine x. Hang on, let's look at it.
That's what we have to do.
Wait.
That's another
integration.
Yeah. All right, let's take a look at this together. U is equal to x squared, and dv is equal to cosine x dx. Now, du is 2x dx, and v, when we integrate dv above, integral of cosine is, very good, sine x. Now I'm going to put the arrow and write x squared sine x minus integral of 2x sine x dx. Now, when you analyze this, observe that this portion of the problem looks very similar to this portion of the problem, which means it's again integration by parts. Nested, which means again u equals, now you can kick this 2 in front, or you can just keep it there as 2x, it's fine. And then dv sine x dx. du is 2dx, and v is negative cosine x. Arrow. So it equals to x squared sine x minus, and now I have to use the bracket because I'll have another subtraction in there, so I just want to make sure my signs are all good. I have negative 2x cosine x, right? That's when I multiply this with this as a uv, minus the integral of 2 negative cosine x dx. So this is your uv minus integral of v du, but with the new u and v, equal x squared sine x plus 2x cosine x plus 2 integral of cosine dx. All I need to do is integrate cosine, which is very good. Plus c. Done deal. Put this on a cloud for Alex.
It's the triple negatives. What am I creating?
Triple negative. Oh yes, there is a negative here, and negative here. It's a triple negative. That is a negative there. It's clearly a negative, see? That's a negative. I don't think I can be clearer than that. It's a negative sign. Yeah, do that in your notebooks. Yes?
So for a case like the integral of dx cosine of x,
That's next. You're in charge, by the way. Yes.
The second line down, why do you write integral 2x sine x instead of integral sine x to x?
It's better if I put 2x in front of sine, because sine has the argument of x, so it just looks weird.
You don't use it in that line?
What happened?
So you don't mix it with the.
Yeah, I don't want that 2x to be considered as a part of the argument of sine.
It's not a rule, it's just like a benefit line thing.
Yes.
More for
Like-
us, not for like the result.
Yeah.
Right now.
Same thing, like, hairstyles and stuff.
Okay, yeah.
Mathematically all the same.
What? No, it's going.
So, can anyone see the connection? Did this click already or didn't click yet?
it's kind of making sense. I think it's just like confusing because it's new material.
So, I have a question. If this over here exponent is to be a 3, how would that change the problem? 3 integration by parts. If it's to be 97, do 97 integration by parts. Very good.
Hopefully there's a way that, let's say you were to do an x to the 97 cosine of x, is there a shortcut or?
There is no shortcut. You actually do 97 integrations by part. After you bury anyone who asked you to do that.
I think like how you bury them and then still go through with the problem.
Oh, it's principles. You still go through the problem because you just, show off to the rest of the world that you're capable. So in the light of that, integral of ln x divided by x to 97 dx. Bring it on. As I thought it.
It's gotta be.
Yeah, he's already done with 3, right? I'm already on my 3rd iteration. You're telling me there's a trick? So, experience, guys, experience will teach you, as you practice thousands of these problems, you probably solved it just by looking at it, right?
Yeah.
Good, because this one is like that. There is a big difference. Go on. These two problems are very different. They have the same ingredients, but they are very different. Integral of x to the 97 times ln x is 97 integration by parts, so that this eventually dies. But over here, this part is in your integral, and you do it only once with this, and you're back to the basic one. One step. So I know it looks bad, but when you get the grasp of this, you will see that these changes, right? Where is this x to the 97? It actually determines which way you do the problem, determines whether you should cry or actually do the problem. So u is equal to ln x, and dv is equal to x to the negative 97 dx. That's 1 over, right? And then du is 1 over x dx, and the v is, well, we add 1. So x to the negative 96 over negative 96. Arrow? So what do I get? I get negative 1 over 96 x to the 96 ln x. Minus and minus will give me plus integral of, and look what we have. Very simple stuff, right? That, well, I'll take 1 over 96 outside as well. And I have integral of 1 over x to the 97, because you have 1x here and 96 on the other end. So as you can see, it's only one integration. That's negative 97, negative 96, so it goes like this. So negative ln x over 96x to the 96 minus 1 over 96 squared x to the 96 plus c. So we had x to the 97, and it was 1 integration by part. Now, if you have the problem as x to the 97 times ln x, good luck.
Is there really no simpler way? Like not even that trick? Yeah, like not even one that we were learning in Calc 2, like something that...
Well, actually, wait, no. This is also simple.
Can you show us?
This is also simple because you're not integrating ln x. They're both simple. They're both simple, actually. Because you would use the same method. You're not integrating ln x. You're differentiating ln x. So it's still simple with ln. You don't want to have it for e to the x or sine and cosine. That's what you don't want to have it. With ln, it's fine. Because ln is the one that flips of which one you pick as your u. So it's bad to memorize because you run into trouble, but in general, sine, cosine, and exponentials, u is polynomial part, and for ln's, ln is the polynomial part because you can't integrate it. Let's see something from the textbook that you might enjoy. Huh. That's what I'm looking at and I really like this one, but I'm afraid of retaliation in the classroom. So we do vanilla and then we do the spicier one. Actually, we don't have time for two because we still have to look at one problem. So let's do a quick calculation. This is perfect one. 1 to e ln 2x dx. Brilliant.
Do we even need integration by points for this one? Do we even need integration by points for this one? Since we know that it's derivative of ln x. I'll take that as enough.
As soon as you said the word derivative, I knew that you're going to catch up on it.
Can we use position things?
I'm sorry?
Can we just use substitution things?
Nope.
Sat down and called my friends. So it's water boiling. I know. It worked. Yeah, well, that's the other thing. I also like to get more pasta. I was very tired. I was tired. I was still thinking.
All done? Since there's too much chatter. Easy, right? U is? Very good. And dv is? Dx. So what's du? Excellent. And what's v? Perfect. Hit the arrow. So now what do I get? I get x ln 2x minus the integral of dx, right? Because 1 over x times x is just 1. We still have 1 to e limits. So that's x ln 2x minus x, everything computed from 1 to e, which is e times ln 2e minus e minus ln 2 plus 1, right?
We didn't need to use integration that much, like we could have done use of like the whole.
But you're still going to have the ln. You'll have ln u. Yes.
No, but didn't we figure out the integration for ln of x is x ln x minus x? So since we know that,
Yeah,
we could use
sure. But you can't forget the 2 in there. Yeah, it's not clear. So now we know, hopefully, properties of logs. And that's 1. So I have e ln 2 plus e minus e. They cancel. And we can factor out ln 2, have e minus 1, and then everything plus 1. The whole thing is like 3. Grand finale for the class. Ready? Ready for the grand finale?
not real.
So we liked so far our integrals which had x and x squared and so on, because in the derivative they eventually die, and you just integrate whatever is there. What happens as you integrate or differentiate into the x? It doesn't go away, right? And how about cosine x? It doesn't go away. So this looks like one of those hopeless problems where no matter how many integration by parts you do, it will always bring back e to the x and cosine x. However, you said you knew something about it.
Yeah. So once it goes back to the x, back to the same side.
You know the trick. So even though we look at this and we claim as hopeless because the functions suggest it will be hopeless, on the second iteration, we will receive the integral like this. And then, because it's equal to blah, 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 and that integral, you move that integral on top of this and then divide both sides by 2. It's a really neat trick. I know. I was, as a student, when I saw that, I was like, someone actually figured this out. Because we are so used to just integrate forward, right? Integrate forward. I'm going to show you something cool once we are done with this problem, just to show you how cool math is. Bazooka? How's that related to this? How is it not? Oh my God. All right. U equals e to the x. I just give up. dv equals, I'm just going to do this and just bail. du equals e to the x, and v is equal to sine x. And we do the arrow thingy. So now what we get is e to the x sine x minus the integral of e to the x sine x dx. And this is about where the desperation starts, because you see that you started with the exponential time trig and you still have exponential times trig. So, you know. But luckily we know that we don't have to panic yet, because we can go and say u equals e to the x dv equals sine x dx. Hold on, cool minute. There we go. Sine x dx, and then du equals, again, dx x. Ooh, I forgot the dx here. Wow. And then v is negative cosine x. Arrow. We have to copy the old e to the x sine x minus, and then we have the bracket where we go and say negative e to the x cosine x, and then minus, and minus gives me plus integral of e to the x cosine x dx. And then we get rid of these brackets. So e to the x sine x minus and minus gives me plus e to the x cosine x, and then minus the integral of e to the x cosine x dx. And this is when we realize that the problem and this part are the same. So you take this and add to the other side. So add this term to the left-hand side. Once you do that, you will have 2 integral of e to the x cosine x dx equal e to the x sine x plus e to the x cosine x. Yeah, divide, well, plus c, and then we'll divide everywhere by 2. So integral is e to the x cosine x dx is equal to 1/2 e to the x sine x plus 1/2 e to the x cosine x plus c. You don't have to put c over 2 because it absorbs.
Why is that C there?
Because of the 2. Are you asking about why is this 2 here? Or why is this 2? 1 over 1/2.
The one before the end, right?
This one.
Where'd that come from?
It came from adding this term
Yeah, this side.
to this term.
Oh, because that's still on the other side.
Yeah, on the other side. So you add apple plus apple is 2 apples.
It's still wait.
Historically speaking. And that's it for integration by parts, but we are going to do more examples after, well, at the beginning of the next class. Let me just say bye to stream. Bye.